Welcome to the debate.
Glad to be here.
So I want you to imagine shining a massively powerful laser into the absolute deepest, emptiest void of space. Just total nothingness.
Okay, painting a picture. I like it.
Right. And then you turn it off. Millions of years after you do that, does the universe remember it was there? Like when light travels through glass or water or even the cosmos, does it have to push its way through?
That's such a profound question.
It really is. And today, we are diving into exactly this, driven by a really fascinating exploratory essay titled The Resistance of Light. And I'll be taking the intuitive perspective here. Basically, if light slows down, bends, and gets weaker as it moves through matter, well, it must be fighting some form of physical resistance.
Right, and I will be taking the contrasting view. Because while that friction analogy is beautiful and honestly super understandable, slowing down is not the same thing as losing energy. Light's journey actually involves interaction mechanisms that are far more profound and honestly weirder than simple physical friction.
But it's just such an irresistible starting point. I mean, it perfectly maps to how everything else in our physical world operates.
It does, yeah.
Think about the electrical analogy. When we send an electric current through a copper wire, those moving electrons, they're constantly interacting with the metal. They are hitting microscopic obstacles.
Right, they're bouncing around the atomic lattice.
Exactly. And in classical physics, that useful electrical energy gets converted into heat. The wire literally warms up in your hand, and we call that electrical resistance.
Yes, a very well understood phenomenon.
So watch what happens when light enters a pane of ordinary glass. It does the exact same things. Its speed drops to, I think about 2/3 of its speed in a vacuum.
Yeah, roughly a refractive index of 1.5, so 2/3 is right.
Right. So on top of hitting the brakes, it bends at the boundary. And if the glass is thick enough, the beam gets gradually weaker over distance. So to my mind, this has to be a form of optical friction. The light is actively pushing against the glass, and the glass is pushing back.
I completely see why that analogy is so tempting. From our macroscopic everyday perspective, it makes total sense.
Right? It's just logical.
It is, because in classical mechanics, if a moving object suddenly loses a third of its speed, kinetic energy has been robbed, usually via heat and friction, like you said. But here is where the story diverges into something quite wonderful.
Okay, color me intrigued.
What looks like simple friction to our eyes is actually three completely different events hiding in plain sight. You've got delay, redirection, and loss. A photon is not, scraping its way through molecular sandpaper.
Molecular sandpaper? That's actually a great way to visualize my argument, though.
It's a great visual, but it's not what's happening. My core thesis today is that in an ideal transparent material, light delays without losing a drop of its fundamental energy. And that completely breaks the traditional rules of friction as we naturally understand them.
Okay, I see why you think that, but let me push back a bit. Because we can't just ignore the drop in velocity.
Fair enough.
If light isn't rubbing against anything like sandpaper, then what is applying the brakes? If it drops to 2/3 of its speed in glass, but it's not radiating heat into the surrounding material, well, if it's not friction, some physical mechanism must be actively robbing it a forward momentum.
Right, I get that. But I come at it from a different way. We have to stop thinking of light as a solid, independent object plowing through a stationary medium.
Okay?
Think of light as an electromagnetic wave passing through a highly responsive crowd of charges. When the wave enters the glass, it interacts with the charged particles in the material, specifically the electrons.
So it hits the electrons.
Well, not hits. The incoming electric field of the light literally pulls and pushes on those electrons, causing them to jiggle or oscillate.
Wait, so the light is physically moving the electrons? That sounds exactly like doing work, which requires expending energy, right?
It does sound like it. But here's the trick. Those oscillating electrons immediately generate their own secondary electromagnetic waves in response.
Oh, interesting.
Yeah. So what actually propagates through the glass is not just the original light wave fighting its way through a barrier.
It is the superposition, basically the mathematical addition of the original wave and all those newly generated secondary waves.
Wow. So the material isn't a wall being smashed into. It's more like an active participant in the wave's journey.
Precisely. It is a combined collective system of light and matter, a coupled system. The reason the light appears to slow down isn't because it's grinding against the atoms and losing energy. It's because the phase velocity of this newly combined wave, this collective dance of charges and fields, is just slower than a wave moving through empty space.
So the choreography just takes time.
Exactly. The choreography takes time.
Okay, I understand the wave addition part, but I am still struggling with the energy preservation.
Sure.
If it is interacting that deeply with the material, doing this complex dance, how does it avoid losing energy to the system?
Because the frequency of the light hasn't changed. The energy of a photon is directly tied to its frequency, not just its speed. And here is the piece of evidence that completely dismantles the friction idea.
Let's hear it.
What happens when the light exits the glass and goes back into empty space?
It speeds back up?
It immediately resumes its ultimate maximum vacuum speed of nearly 300 million meters per second, instantly.
Right.
If that light had been fighting friction, it would have permanently lost energy to heat. It would exit the glass permanently weakened. But because it was simply a delayed wave choreography, the moment it leaves the electrons behind, the original wave continues exactly as energetic as it was before it entered.
Okay, I will concede that a flat piece of glass might just be a complex delay mechanism for a wave moving in a straight line.
Progress.
Yeah. You can explain away straight line speed using wave addition, but that only works in a straight line. What happens when we force light to turn a corner?
Ah, a great question.
Let's look at the optical roadways we use every day, right? Fiber optic cables.
Right, internet cables.
Exactly. Inside an optical fiber, light isn't just going straight. It is following the curves of the cable, bouncing off the internal walls. You cannot turn a corner without hitting a wall. If it is changing direction continuously like that, it must be exerting physical force against the glass core.
That is a highly compelling argument. And honestly, this is where your intuition about light pushing is absolutely correct. Light does push.
Wait, really? You are telling me a massless particle exerts physical force on a solid glass wall?
I am.
How does something with absolutely zero weight push a physical object? That sounds, mathematically contradictory.
It is one of the most counterintuitive facts in modern physics. Photons have no resting mass, but they absolutely carry momentum.
Momentum without mass?
Yes. We have to separate the concept of momentum from our everyday experience of heavy objects, like bowling balls. Momentum at the quantum level is fundamentally related to a wave's energy. In a vacuum, a photon's momentum is simply its energy divided by the speed of light.
So it is not a heavy physical object colliding with the wall. It is pure, massless, energetic momentum transferring force.
Exactly. And we can see this brilliantly in a curved optical fiber. When you bend that cable, the light's momentum must continuously change direction to follow the curve.
Like a car on a track?
Yes. Think of a high-speed race car taking a steeply banked turn. The car wants to go straight. The curved wall of the track has to supply an inward force to change the car's direction.
And Newton's third law says there must be an equal and opposite reaction. So if the glass track is pushing inward on the light to turn it, the light must be pushing outward on the glass track.
Perfectly stated. The glass supplies the inward force to curve the path, and the light supplies an equal reaction force pushing toward the outside of the bend.
That is incredible.
It is a minuscule push, to be clear. We are talking about radiation pressure measured in nanonewtons per watt. You could never feel a fiber optic cable twitch in your hand from the data flowing through it.
No jumping cables. Got it.
Right. But the force is entirely real. A flow of light is a flow of momentum, and turning it requires physical force.
Okay, so if the light is physically pushing against the outside of the curve with real momentum, what happens if I bend that fiber too sharply? Does the optical race car just crash through the wall?
It absolutely does.
No way.
Seriously, if you bend the fiber too sharply, the momentum is just too great for the curve. The light literally fails to make the turn and escapes the glass rod entirely, bleeding out into the surrounding material.
Oh, wow.
Yeah, this is why technicians have strict minimum bend radii for fiber installations. They aren't just protecting the fragile glass from snapping. They're actually managing the physical momentum of the light to keep it on the road.
So we have established it pushes against glass. It exchanges momentum with matter, and it requires physical force to change direction.
We have.
But what if we remove the matter? I still maintain that light faces a form of resistance, even in a vacuum.
Oh, here we go.
Hear me out. If I shine a tremendously powerful laser through the absolute emptiness between galaxies, what happens? Does empty space act like an invisible jelly that resists the light? Does space itself remember that the laser passed through?
I am sorry, but I just don't buy the invisible jelly theory.
Come on!
I mean, for a long time, physicists did believe in something like that. They called it the luminiferous ether, assuming space had to be filled with a physical substance for light to travel through. But the vacuum is not an ether. Light does not push through space like a bullet pushing through the air, creating a wake.
But you just proved to me that light has energy and it has momentum. If a phenomenally powerful burst of light travels through the vacuum, all that energy has to interact with something. Are you saying empty space is completely immune to the physical reality of a megawatt laser?
Ah, now you are touching on the profound reality of Einstein's general relativity. Classically, sure, empty space doesn't care about the light. But general relativity tells us that gravity isn't just a force pulling masses together. Gravity is the geometry of space-time itself.
Right.
And what dictates that geometry? Not just mass, but the energy-momentum tensor.
Wait, so because light carries energy and in momentum, it actually interacts with the gravitational geometry of the universe?
Yes. Energy density curves space-time just like mass does. So if you have a massive, intense burst of radiation flying through empty space, it doesn't leave a trail of heat or a worn-out corridor, but it can leave what physicists call a gravitational memory.
Gravitational memory. What is the actual mechanism of that? How does massless momentum permanently alter empty space?
Think of the geometry of space-time, not as an empty room, but as a tightly woven fabric. When a cataclysmic, asymmetrical burst of energy, like a massive gamma ray burst, snaps through that fabric, it creates a gravitational ripple.
Okay.
But as the ripple passes, the fabric doesn't return to its exact original weave. The passage of that immense energy permanently shifts the metric of space-time.
So if I were to measure that space before and after...
Exactly. Imagine two tiny asteroids floating perfectly still in deep empty space. A massive burst of radiation passes between them. Long after the light is gone, millions of years later, you measure those asteroids again. You will find their relative positions have been permanently displaced.
That is staggering.
The actual distances between points in that region of space have shifted. The geometry of space-time itself retains a historical after-effect of that energy passing through.
That is, wow. So the light didn't rub against space with friction, but it actively warped the structural architecture of the space it was traveling through?
Exactly.
Which actually brings me to the ultimate test of this theory.
Oh boy.
If intense light can push matter in a fiber optic cable, and if it can permanently warp the geometry of space-time in a vacuum, then let's look at the ultimate origin of light.
The Big Bang.
The Big Bang. If an intense beam can leave a memory on the void, then the Big Bang must have been the ultimate burst of radiation scratching its way through the universe.
It is the ultimate laboratory for extreme physics. But I have to gently correct the imagery here, because it is one of the most famous misconceptions in science.
What do you mean?
The Big Bang was not a massive flashbulb exploding into a dark, empty room.
So there was no void for the light to shoot into? What was it shooting through?
There was no pre-existing empty space waiting to be filled. The early universe was an intensely hot, incredibly dense soup of plasma, and it was hot and dense everywhere all at once. Space itself was expanding, but the space was filled with this material.
So the light was trapped.
Yes.
Wait, if the early universe is just a dense soup of matter, then my intuition about light constantly crashing into things and facing physical resistance is entirely accurate for the first era of the cosmos.
100% vindicated.
Yes.
In that early plasma, photons couldn't travel more than a microscopic fraction of a millimeter before colliding with a free electron. This process, it's known as Thomson scattering, meant the light was in a state of continuous violent interaction with matter, bouncing like crazy. The universe was completely opaque.
And because of that constant crashing, that constant exchange of momentum we talked about earlier in the cables, that trapped radiation must have been exerting an unbelievable amount of physical force on the early universe.
Immense force. The radiation exerted such intense pressure that it actively drove massive sound waves through the plasma.
Sound waves made of light pressure?
Essentially, yes. Baryon acoustic oscillations. This wasn't just light illuminating a scene. The physical pressure of the light was pushing matter around, creating vast ripples of high and low density.
So the physical momentum of the light actively sculpted the universe. It dictated where matter would eventually clump together.
Yes. Those density ripples eventually became the seeds for the large-scale structure of the universe. The way galaxies are clustered together today across billions of light years is a direct structural memory written into the cosmos by the physical pressure of ancient light.
That is just incredible. But eventually, the universe expanded and cooled, right? What happened to all that trapped bouncing light when the plasma state ended?
Well, about 380,000 years after the beginning, the universe cooled, just enough for those free electrons to bind to protons. They formed the first neutral hydrogen atoms.
Okay.
And suddenly, the matter stopped scattering the light.
The dense fog finally cleared.
The fog cleared. The universe became transparent almost instantly on a cosmic timeline. And those photons, which had been trapped in a state of constant collision, finally began traveling freely through the newly transparent space. And well, they have been traveling ever since.
Wait a second. Are you talking about the cosmic microwave background? Like the faint background temperature of space?
I am. The universe is bathed in a faint microwave radiation, sitting at a temperature of about 2.7 Kelvin above absolute zero. For a long time, it was easy to think of this as just an echo, or like a thermal trace left behind by the Big Bang.
Right, an echo.
But it is not an echo. It is the ancient light itself.
So when astronomers point a microwave telescope at the empty sky, they aren't looking at a scar left by light. They are looking directly at the exact same photons that were released the moment the universe first became transparent.
Precisely. It is the original light. The only difference is that as the universe has expanded over the last 13.8 billion years, the space itself has stretched.
Ah, and the light stretched with it.
Exactly. As the space stretched, it stretched the wavelength of those traveling photons along with it, shifting them from visible, high-energy light all the way down into the invisible microwave spectrum.
Wow. That fundamentally reframes our entire discussion. You know, I started this conversation stubbornly insisting that light faces physical resistance.
You were very stubborn about it.
I was. And while I will concede that it doesn't behave like classical friction in a copper wire, it doesn't lose kinetic energy to heat when it slows down in glass, I still maintain my core intuition.
Which is?
The constant exchange of momentum with matter, the bending of space-time geometry, and the sheer physical force it exerted in the early universe. All of that proves that light experiences profound physical interaction and resistance. It is not just flying through a passive void.
That is a completely fair perspective, though I would frame it differently.
Of course you would.
Well, using the word resistance implies a battle, right? A grinding attrition against nature. I think abandoning the friction analogy reveals a much more elegant reality.
Elegant how?
It is a delicate, lossless interaction. We live in a universe where light delays without losing its fundamental energy, where it gracefully exchanges momentum to navigate the curves of an optical fiber, and where it exists in a constant dynamic conversation with the geometry of spacetime itself.
It is a semantic tension we might just have to leave unresolved. but I think it unites both of our perspectives on the sheer physical reality of light.
I agree.
Light doesn't just passively travel through the history of the universe as a silent observer. Its momentum and its energy help actively write that history. From the formation of galaxies in the early plasma to the data flying around the curve of a fiber optic cable in our modern cities.
It is a wonderful thing to realize. Matter, geometry, and light are bound together in a way that defies our simple everyday intuitions.
It really makes you look at the everyday world differently. Tonight, when you are at home, just turn on a lamp and look at the light filling your room. It isn't just illuminating the air. It is interacting with the glass of the bulb. It is pushing ever so slightly on your walls, and its journey is bound by the exact same physical principles that shaped the dawn of time itself.
A truly beautiful way to see it.
Thank you all for joining us on this intellectual journey today. We will leave you to ponder that tension between interaction and resistance, and we'll see you next time.